Hello, my name is Dan Eaton, and this presentation will introduce you to Amazon EC2 F1 instances and prepare you to go through a hands-on lab using F1 and Xilinx SDAccel development environment. During the presentation, I'll give you an overview of Amazon EC2 F1 instances and Xilinx SDAccel development environment, speak to the F1 hardware and software stacks, show you how to create kernels and compiling the FPGA, develop and execute a host application, and finally show you how you can get started using F1 today. First things first, Amazon EC2 F1 instances are an elastic cloud computing instance combining x86 CPUs and Xilinx FPGAs to create and run accelerated applications. The FPGA serves as a high-performance accelerator to the x86 CPU. F1 instances come preloaded with all the necessary development tools to create, optimize, and program the FPGAs. Once the desired FPGA program is ready, it can be deployed in a few clicks on a number of FPGA instances, providing elastic compute acceleration in Amazon. There are three main ways that F1 is utilized. Hardware developers can use F1 to develop and deploy custom FPGA accelerations using Verilog and VHDL. Software developers can use OpenCL to build custom accelerators from C and C++ code, and AWS end users can use pre-built, ready-to-use accelerators available in the AWS Marketplace and on GitHub. Amazon EC2 F1 instances are currently being used to accelerate machine learning, video streaming, genomic sequencing, analytics, financial computing, engineering simulations, image processing, security, compression, and many more. But any compute-intensive application that benefits from massive parallelism and deep pipelining is a good candidate for F1. Here are a number of the F1 accelerated applications in the AWS Marketplace. On the bottom of the slide is a hyperlink to more F1 apps and libraries. The Xilinx Accelerator program is for organizations that are building FPGA-accelerated products or services in the cloud. The program offers partners technical support and access to co-marketing and financing opportunities. F1 makes FPGA acceleration available to a large community of developers who would not otherwise have the resources to create their own acceleration architecture. F1 makes FPGA acceleration available also to millions of potential end users who will be able to tap into a broad marketplace of acceleration-ready apps. F1 instances come with one or more high-end FPGAs, each providing a vast amount of programmable logic. This allows for creating massively parallel FPGA accelerators that deliver orders of magnitude increases in application performance and throughput. Programming the FPGAs require dedicated tools, compilers, and debuggers. Amazon has partnered with Xilinx to simplify the development process by providing cloud-based FPGA development tools, effectively democratizing the FPGA programming process. Finally, the Amazon Marketplace provides a game-changing way of deploying and monetizing FPGA applications. Software developers and FPGA designers can now create new and innovative accelerated applications and put them in the marketplace and enable millions of end users without having to manufacture and ship actual systems. Now that we've covered the basics of the F1 platform, let's take a look at the F1 development process and the app publishing flow. Because F1 is a cloud computing instance, development can also happen in the cloud. Developers start by logging into AWS and then select an instance preloaded with FPGA Developer AMI. AMI or AMI stands for Amazon Machine Image. It designates the initial configuration installed on the selected machine. In this case, the FPGA Developer AMI provides all the necessary tools to develop the FPGA program on the selected cloud instance. The developer can then use these tools to design, debug, and optimize both the FPGA program and the host application in the cloud. Once the final app is ready, it can be published on the AWS Marketplace as a new AMI. But it's important to know that the development on the cloud is not the only option. Amazon also makes it possible to develop on-premise, that is, in your own environment. All the tools and files needed to develop on F1 can be downloaded and installed locally on your own machines. The development process in the cloud or on-premise is strictly identical. Once you've completed development of the FPGA program and of the host application in your environment, you can upload both binaries to the AWS cloud, execute on F1, and publish your app in the Marketplace. Now let's look a little bit more at the development tools. There are three main development flows on F1. RTL custom design with RTL-centric flow using AWS HDK scripts. This flow also provides RTL simulation for the kernel, has a custom API for the host code, and directly leverages Xilinx Vivado toolchain. The second flow is SDAccel C++ with OpenCL API. This flow is F1 platform aware. It uses pre-built communication infrastructure. It's an integrated development environment that's fully C-based, and it has a quick setup, run, profile, and debug capability. The last flow is the SDAccel flow with an imported RTL kernel. This flow is F1 platform aware, uses pre-built communication infrastructure. The host code is managed in SDAccel, and it also allows for reuse of high-efficiency RTL accelerators. Let's look a little bit closer at the custom logic design flow with the Amazon HDK. The Amazon HDK provides scripts to build an AFI, RTL, and this option also provides the option to use the Xilinx Vivado IPI or IP integrator and or HLS. The custom logic CL is the user accelerated container. The AWS shell or SH wraps around the custom logic or CL. The AWS HDK compilation will build a fully implemented design checkpoint file, which then becomes an AFI. Now let's look at the SDAccel flow that users can use. The SDAccel flow also offers developers the ability to develop, profile, and deploy OpenCL applications. OpenCL uses standard APIs, which means the code itself is highly portable. This flow is F1 platform aware, and it allows for very flexible kernel development in C, C++, OpenCL, or RTL. Looking at the SDAccel with RTL kernel flow, users can import RTL through a kernel wizard in SDAccel. Note that the top level needs to match the interface requirements. With this flow, developers can leverage existing RTL IP, which is likely very resource efficient and high performance. Hardware emulation mode is also available for simulation. Here's a table that provides a high-level comparison between the three F1 development flows. Now let's look a little bit closer at SDAccel. As we've established, F1 is a compute instance combining an x86 CPU and a Xilinx FPGA. SDAccel provides all the necessary tools to debug, compile, and profile and execute an accelerated application running on AWS. The host side application, here shown on the left-hand side, is developed using standard C or C++. The FPGA on the right-hand side can be programmed using traditional RTL code, also using C, C++, or OpenCL. This flexibility is key to enabling a wide community on F1. With the RTL flow, SDAccel allows existing RTL designers to capitalize on their skills, reuse their IP, and leverage them in the cloud with minimal effort. With the C and OpenCL flow, SDAccel opens FPGA programming to software and algorithm developers. SDAccel is a fully integrated Eclipse-based environment. It provides all the necessary features to develop, profile, and deploy applications on Xilinx FPGAs. Using SDAccel, developers can concurrently develop the host application and the FPGA kernels and execute the two together when ready. The tool offers different testing and execution modes, providing various levels of debug visibility. In addition, SDAccel provides comprehensive profiling and performance analysis tools which can be used through the development and testing process. These features are important to help developers tune their applications. During this section, we'll look at the F1 hardware and software stacks in more detail. The primary motivation for running on F1 is to accelerate compute-intensive and performance-sensitive applications and workloads. On F1, acceleration works by offloading a portion of the compute-intensive and deeply pipelined parts of your application to the FPGA, where customized hardware accelerators provide the needed performance boost. The rest of the application executes on the x86 host CPU. Communications between the CPU and the FPGA is carried out over PCIe. In the next few slides, we'll look in more detail at that communication from the CPU to the FPGA and how it actually works. Here's an abstracted model of the F1 platform. On the left side, in the gray box, we have software stack running on the x86 CPU. On the right-hand side, in the red box, we have the hardware components in the FPGAs. On the host CPU, the custom application interacts with the FPGA using the OpenCL API. OpenCL is an industry standard providing clear semantics for parallel computing. The OpenCL runtime is responsible for managing and servicing the various accelerator requests sent to the FPGA. At the lowest level, the drivers handle the PCIe transfers between the two devices. The FPGA sits on the receiving end of these PCIe transactions. The F1 FPGA comes preloaded with all the necessary logic to DMA the data to local DDR memory. The custom accelerator kernels can then read the data, process it, and write it back to DDR using standard AXI interfaces. F1 exposes clear and standard interfaces for the app developer. Everything below this line comes off the shelf with the F1 platform. Everything above the line, host code and hardware kernels, is provided by the developer of the accelerated application. Amazon and Xilinx have tightly collaborated to make this platform as performant, robust, and easy to use as possible. By using standard OpenCL and AXI interfaces, F1 hides the complexity involved in building a heterogeneous platform and lets developers focus on what matters most, accelerating their code. Speaking of accelerated applications, here's an abstract example of how one may look. In this example, we're looking at an HEVC video encoding app. HEVC, also known as H.265, offers an average bitrate reduction of 62% for 1080p frames compared to H.264. With the advent of online video streaming, high-efficiency video codecs such as HEVC are in high demand. Unfortunately, HEVC encoding is a compute-intensive task, and neither CPUs nor GPUs offer enough horsepower for this task. Here's where F1 comes in. The Xilinx FPGA is an ideal platform for video acceleration. Custom data paths can be created to parallelize and pipeline the video encoding process. On x86, the app developer can create a custom FFmpeg plugin which will offload the HEVC encoding requests to the FPGA. Creating acceleration plugins for widely used programs and frameworks such as FFmpeg is a very powerful proposition. With this approach, end users can keep working with the programs and tools that they use every day and have F1 accelerate their jobs transparently. As mentioned previously, the F1 FPGA comes pre-configured with hardware functionality to manage communication to and from the FPGA. The hardware layer is commonly referred to as the F1 shell or SH. The shell abstracts the FPGA IOs and presents a standard AXI interface to the kernels. The shell also includes features ensuring the reliability of the platform and the security of the hardware IP. The shell has been thoroughly tested and has been designed for optimal performance. Another central concept to the F1 flow is the Amazon FPGA image or AFI. The AFI designates the program running on the FPGA. It's effectively an image of what is in the Amazon FPGA. Since a lot of proprietary IP is likely to go onto the FPGA and therefore into the AFI, Amazon provides a highly secured mechanism to manage and access these files. All AFIs are encrypted, and the F1 system works in such a way that end users of the application never have direct access to the AFI. Ultimately, AFIs can be associated with AMIs or Amazon Machine Images and offered in the AWS Marketplace, allowing developers to monetize their acceleration IP. Later, we'll discuss in full details of kernel development and AFI creation. After this look at the hardware components, let's now review the host-side execution stack. As mentioned earlier, the stack is based on OpenCL, an industry standard for parallel computing. OpenCL follows a master-slave model which cleanly separates the application code from the kernel logic. Using the OpenCL API, the host application transfers data and submits tasks to the acceleration logic in the FPGA. The OpenCL runtime dynamically schedules and orchestrates the communication between the host and the FPGA. OpenCL has been designed specifically for heterogeneous computing, which is a perfect fit for F1. OpenCL has been designed to be platform independent, which makes the code highly portable across CPUs, GPUs, and FPGAs. Because it's open and standard, you'll find a lot of learning resources online. If you're not already familiar with OpenCL, a simple Google search will return many links to trainings and examples. Another key advantage of OpenCL is its runtime. This runtime manages all the communications between the host and device and takes away the bulk of the complexity of optimizing parallel computing applications, which can deliver faster time to results. Lastly, one feature of OpenCL is the ability to dynamically swap and load different kernels. This means that on F1, your application can start using the FPGA to accelerate a particular workload, and then on the fly, load a new AFI to accelerate a different type of workload. For all these reasons, OpenCL is a natural choice for the F1 platform. To summarize what we've covered so far, the FPGA program is compiled, encrypted, and registered as an AFI. The host application, for example, a framework plugin that interacts with the FPGA using OpenCL. Once you have the two working together, you're ready to create and publish your own AMI. And this will allow end users to start their own F1 instance loaded with your AMI and have instant access to your accelerated application. Amazon provides various pricing models and offers a lot of flexibility and a rapid path to monetization. In this section, we'll cover creating kernels and compiling the Amazon FPGA image. The AFI creation process is broken down into 3 steps. First, the kernel creation phase. Here you'll be using SDAccel to create kernels from either C, C++, OpenCL, or RTL models. Next, you'll be compiling the platform. Here, the SDAccel compiler is used to link together the previously created kernels with others required hardware components and generate the FPGA binary. Finally, a special AWS service is used to create, encrypt, and register the AFI. We will now look at these steps in closer detail. As mentioned earlier, kernels can be created from either C, C++, OpenCL, or RTL code. Let's start by discussing the RTL flow. This flow caters to existing RTL designers and allows them to reuse existing RTL code. To be used on F1, existing RTL code must be packaged as SDAccel compliant kernels. This primarily means complying with specific interface requirements. For best results, it's recommended to design RTL kernels with F1 specs and app performance goals in mind. To facilitate the RTL kernel design and packaging process, SDAccel features a wizard that guides the user through an interface definition step. The output of this packaging flow is a .xo file. This is a container file which includes the information needed by SDAccel to use the kernel. Just like C code can be compiled in a .o object file and later linked to produce the final executable, kernels can be packaged as an XO file, which are later linked to produce the FPGA design. The XO files are effectively the key building blocks used by SDAccel to assemble the FPGA design. Kernels can also be created from C, C++, or OpenCL code. This flow is well suited for software and algorithm developers. It makes it easier to start with existing C and C++ applications and accelerate portions of them. SDAccel provides a special parallelizing compiler which synthesizes high-performance kernels from C, C++, and OpenCL. The SDAccel compiler is able to extract parallelism from loop structures and has built-in optimization tuned for Xilinx FPGAs. A good analogy is to think of a cross-compiler that targets a special type of architecture. The output of the cross-compiler is a kernel packaged as a .xo file. The SDAccel compiler supports a rich set of C, C++, and OpenCL constructs. When it comes to OpenCL, the compiler specifically supports OpenCL 1.0 embedded profile, OpenCL 2.0 pipes, and OpenCL 2.0 image objects. Kernels can be expressed with n-dimensional ranges, and many convenient vector types can be used for SIMD optimizations. The code on the right-hand side shows a simple OpenCL matrix multiplication example. More than 80 examples of synthesizable C, C++, and OpenCL can be found on the SDAccel GitHub repository. These examples are a good way of getting familiarized with how writing good code for FPGA acceleration works. After the kernels are created and packaged as XO files, the next step is to assemble the FPGA design. Remember that the kernels and the XO files are just building blocks. They need to be integrated with other hardware components such as the F1 shell. In this phase, the SDAccel compiler reads in the XO files and automatically instantiates the kernels and the F1 shell. It then automatically generates the DDR interfaces and creates AXI interconnect logic. Lastly, the compiler makes all the necessary wiring and connections. This results in a completely assembled FPGA design. After that, SDAccel runs the FPGA implementation flow. This is known as synthesis, placement, and routing. The result of this FPGA binary is in the form of an XCL bin file. It's important to keep in mind that multiple iterations might be needed to converge on an optimal design. The Xilinx ultra-fast methodology guide is very useful for achieving the best results. The final step here is to create the special AFI or Amazon FPGA image. Here, the XCL bin is converted to an encrypted AFI using a special AWS service. The resulting AFI is securely stored by that backend service. The AFI can be identified and accessed using a unique AFI ID. This ID is written in the AWS XCL bin file, the cylinder in this diagram. The AWS XCL bin is what gets shared with app developers and app end users. It only contains the AFI ID. All sensitive FPGA design IP is securely stored. With the AFI ready, you are now ready to turn your attention to the host application. During this section, we'll learn about developing and executing a host application on F1. The development flow for the host application can be broken down into 3 steps. In the development phase, you'll be adding OpenCL calls where necessary to interact with the FPGA. Then you will compile and execute the application with the FPGA kernels. Finally, you will use SDAccel analysis tools to profile and optimize your code. The host application is written in C, C++, and is compiled with GCC. This process will be very familiar to many programmers. What distinguishes an F1 app from a standalone program is the use of the OpenCL interaction with the attached FPGA device. At a high level, there are 3 main things the developer needs to think about. 1, setting up the FPGA. 2, passing data to the FPGA and executing kernels. And 3, releasing the FPGA when the program returns. OpenCL provides the necessary API to do these things. There are, of course, various optimization considerations. One thing to note is the host application can ultimately take many forms. It can be a standalone executable, plugin, a shared library as we discussed in our FFmpeg example. It can be architected as a client-server system where multiple clients would submit acceleration requests to a server. There are lots of possibilities, certainly one for every need. As we saw, the host application is responsible for setting up the FPGA. When the application runs, it starts by loading the AFI ID with the AWS XCL bin file. It then contacts the AWS storage with the ID and then downloads the proper AFI in the FPGA. The platform is now configured and ready to go. This setup step can be repeated multiple times during execution. This will result in the application dynamically swapping and replacing the AFI during runtime. Potentially a useful capability. Executing the application with the actual FPGA is the end goal, but SDAccel provides 3 different execution modes serving different testing needs. Besides the hardware execution mode where you run on the actual FPGA, there are 2 other modes where the FPGA is abstracted and virtualized. In the first mode, the CPU emulation mode, the application runs with a C or OpenCL version of the kernel. This makes for very short and convenient iterations. You will want to run in this mode to confirm the functional correctness of the system. The second emulation mode is the hardware emulation mode. Here the application runs with an RTL simulation of the kernels. Because this mode relies on RTL simulation, it's the slowest, but it is great to test the host kernel integration to get performance estimates and debug insight. Regardless of which execution mode you're using, you will be using the SDAccel debug and analysis tools to inspect, assess, and profile your system. The tool lets you visualize many things such as host and device events, OpenCL API call sequence, kernel execution sequence, FPGA AXI transactions, kernel start and stop signals, and more. In addition, report files such as the profile rule checks highlight performance issues and provide improvement recommendations. These tools provide valuable insight and will help you get from an initial functional app to an optimized and highly performant one. Thank you for watching today.